Hi Year 12, this is our second lesson for the topic of transformations. In this lesson we're going to look at dilation. So last lesson we reviewed how to graph a function and then we looked at vertical and horizontal translations. So graphs can be dilated either horizontally or vertically, and we also call this stretched or compressed. And there will be a scale factor associated with the dilation. So you would have covered scale factor back in Year 9 when you were studying similarity. But recall, we calculate the scale factor by dividing an image length, so say here, by a corresponding pre-image length. So just using a ruler, this is 4 centimeters, and here we have 3 centimeters. And so our scale factor in this case is 4/3. And if the scale factor is greater than 1, it means it's getting bigger. So if I had the shapes the other way around, then I would do 3/4. And a scale factor less than 1 means it's getting smaller. Okay, let's return to our dilation of functions. If we have y is equal to f of x, then y is equal to p multiplied by f of x will dilate the graph with scale factor p. So what does that mean? If p is greater than 1, it's going to make the graph stretch vertically. So you can see that's here. So here's our base graph, y equals f of x. If I put a 2 in front of it, I'm going to stretch it vertically. If p is in between 0 and 1, it's going to make the graph compress vertically. Now, with horizontal dilation, we're going to put the constant in with the x rather than out the front. But we have an added complication here. So if we've got f of qx, that's going to dilate the graph with scale factor 1/q. And this takes a bit of time to get your head around it, and I suggest you go and have a play with it on Desmos and just see what's happening. But if q is greater than 1, like here, it's going to compress the graph horizontally, so it's going to compress it down in this direction. Whereas if q is in between 0 and 1, it stretches the graph horizontally. Now if you want to have a look at why this happens, our original graph here is y equals the square root of x. Let's have a look at y equals the square root of qx, and we're going to turn it around and make x the subject. So square both sides. Y squared is equal to qx. X is equal to 1/q y squared. There's our 1/q. We haven't done a lot of work on horizontal dilations prior to this. And the reason is, many of the functions that we have been dealing with, the dilation could be written horizontally or vertically. Vertically is much easier, that's why we've focused on it. One function that does have a distinct horizontal dilation is a trig function, and we'll have a look at that later on in the video. But let's have a look what I'm talking about. What vertical dilation of the graph f of x is equal to x squared will give the same result as a horizontal dilation of scale factor 1/2. So let's start here. If we want a horizontal dilation with scale factor 1/2, I'm going to put 2 in with this x like this. So f of 2x is the same as 2x all squared, which is 4x squared. Can you see how it's changed from being a horizontal dilation to a vertical one? And the vertical dilation has scale factor 4. So in the past, we have just written it like this. We haven't bothered to do a horizontal dilation because it's overly complicated. Okay, let's look at a couple of examples. Find the equation of the transformed function if f of x is equal to x squared plus 1 is dilated vertically with a scale factor of 3. Now this is really easy. We've just got to put the 3 in front of the f of x like this. So that's the same as 3 outside of x squared plus 1 in brackets, or 3x squared plus 3. Now horizontally with a scale factor of 2, this is where we want to put 1/2 in with the x. So we want f of 1/2 of x. So everywhere we see an x in the function, we're going to put 1/2 of x in brackets like this. And squaring that out, we get 1/4 x squared plus 1. Example 2. The point 4, -2 lies on the graph y equals f of x. Find the coordinates of the image point if f of x is dilated vertically with scale factor 2. So vertically, that's going to affect the y coordinate. And we have a scale factor 2, so we want to make it 2 times as big. So the new point is going to be 4, -4. This is what it looks like graphically. Here's our original point, 4, negative 2. We've stretched it out and it becomes 4, negative 4. How about horizontally with a scale factor of 2? A lot of people will muck this up. They'll think, I've got to turn that into a half. But that's only if you're putting it into the equation and trying to form the equation. Scale factor of 2, if this number here is bigger than 1, it means make it go bigger. Horizontally is our x-coordinate. So the answer here is 8, negative 2. And here it is graphically. Here's our original point, and I've stretched it out. It becomes 8, negative 2. I said we'd have a look at some trig functions because horizontal and vertical dilations are far more intuitive with trig functions. Now, for some functions, like trig functions, the horizontal and vertical dilations cannot be interchanged. Do you remember when we did that back with the parabola and we were able to write it as a horizontal dilation and as a vertical dilation, the same function? We can't do that with trig. So let's describe the horizontal and vertical dilations of this function. Y is equal to 2 sine of 3x. We'll start with the vertical one because it's always the easiest. What does this 2 do? It stretches it out, doesn't it? Sine normally goes between negative 1 and 1. This 2 here will stretch it so it goes between negative 2 and 2. So we have a vertical dilation, scale factor 2. We also know that that's the amplitude. Now what about this? What does that 3 do? It compresses it, doesn't it? It makes sine x go 3 times as fast. So it compresses it horizontally, and there's your third. There's a horizontal dilation there. Scale factor 1/3. This, of course, affects the period. And there's our graph there. So the green one there is the normal sine curve. You can see we've stretched it out vertically and compressed it horizontally. Let's finish off with a past HSC question. Consider the graph of y equals f of x as shown. Sketch the graph of y equals 4 times f of 2x, showing the x-intercepts and the coordinates of the turning points. All right, we have two dilations here. We have a vertical dilation of 4 and a horizontal dilation, scale factor 1/2. So let's start with this 4. This is going to stretch all the y coordinates 4 times. So this negative 8 becomes negative 32. Now this horizontal dilation, this is going to halve all of the x coordinates. So the 4 becomes 2, the 6 becomes 3. Now we don't need to be too accurate when we're drawing this, but we do need to show all these significant points. So this is 4 here. We're going to cut through the x-axis at 3, and we have a turning point at 2. And it's at 2, negative 32. So I want to come down skinnier than that graph there, down through this turning point, and then up through 3. And let's label our turning points 0, 0, and 2, negative 32. Okay, that's it. Our next lesson is on reflection.